So now let me come to the topic. Just a moment, let me change the option. Yeah. So as this was, this KPT sir already gave the introduction that we will be talking about first order, but not of the first degree equations now. Now see, the general form for this class of equations may be written as a function of x, y, dy, dx equal to 0. Because what are the things we are going to have in our equation? The independent variable x, the dependent variable y, and only the first order derivative, because we are talking about first order equations. So dy dx. So only the things what we can have in our equations are x, y, and dy dx. But yes, mind it, I can have a dy dx whole square, or I can have a dy dx whole cube in our equation, because my equation now need not be of first degree. Basically, we would be focusing on higher degree equations. And as again already mentioned, this is a very standard notation that we write P for this dy dx, this derivative dy dx, we write this P. So therefore, in another way, we can say that the equation is written as some function of x, y, p equal to 0. Okay, now actually the solution, when we look into the different categories as it is mentioned here, so what happens is, as if we are treating p is another variable, although it is dy dx in disguise, but as if now I have a function depending on three variables, x, y, and p. And now there are three categories that either we will solve the equations for p, that means p will be your dependent variable or the unknown, or the type 2, that equation solvable for y, or even a type 3 when we will take x as the dependent variable, equation solvable for x. So we will see them one by one. It will take some time for you to understand this case. Sorry, just a minute. By mistake, I stopped sharing. Just a moment. Please give me a moment. Yes. So that is the thing, that we will learn three categories or three ways of solving this equation, function of x, y, p equal to 0, where we will definitely remember that p stands for dy dx. Now, there is a fourth kind, Claudius equation, which has a very special form, y equal to px plus fp. Now, actually, this is not out of the three categories. As you can see here, y is written as a function of x and p. So actually, it is a special situation, very special situation of type 2 case. But anyway, we will do it later. Let us start with the type 1 case. Okay. So now the type 1 equation solvable for p. Now what we think over here, that as I wrote, as we saw here, that I have an equation depending on x, y, p. Say, for example, maybe I have an equation like p square minus 2px plus y equal to 0. Maybe you are given an equation like this. P square minus 2px plus y equal to 0. Now, of course, we should remember that this means actually dy dx whole square minus 2x dy dx plus y equal to 0. Now, when I write this like this, you see that can I not think of this as a this one, p square minus 2px plus y, as a polynomial in p? A second degree polynomial can be. So this is the idea behind, basically. When I have an equation involving p square, we can imagine this as a second degree polynomial in p, and then we should be able to factorize into two linear factors. If I give you an equation with p cube, say something like involving p cube, then it is a polynomial of degree 3. And then we should be able to factorize into 3 factors. So this is basically the idea behind. Now, the most general thing that if I have a polynomial of degree n, that means if you're in your equation, you have a dy dx to the power n. So if I have a polynomial of degree n, then it should be expressible as a product of such n factors in linear factors. So p minus some function of xy, because see what your equation contains, x, y, and p. So therefore, this should be expressible as or reducible as in this form, where we are actually factorizing the equation as product of n factors, like p minus f1 xy, some function of xy, another factor p minus f2 xy, another factor p minus f3 xy, like this. If your equation is of degree n, if it contains dy dx to the power n, then it will be reducible as product of n factors, right? So the general form of any one factor, I can say it is p minus fi xy equal to 0, where I can vary from 1 to n. Right? Is that okay with all? Up to this?
Yes,
ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
So now
Yes, ma'am.
actually what is happening? Now your equation is some polynomial, this f of xyp equal to 0, and this f of xyp, just a moment, I think there is some noise at someone ends. Let me mute all people. Just a moment. Okay. Sorry. Yeah. So please see now what we do is now that this f of xyp equal to 0, we are factorizing it into as a product of n factors. Now each factor, if you look into any one, p minus fi xi equal to 0, where I can be any 1 to n. So we look into any one. Is it not a linear equation? Because what is p? P is nothing but dy dx. So p minus fi xy equal to 0. That is actually nothing but dy dx minus fi xy equal to 0. So it is like, it is actually dy dx is equal to some function of xy. Is it not the first form we learned in our first day for a first order, first degree equation, right? So now if we have reduced this equation as product of such n lead factors, and each factor gives you now a first degree equation, we know how to solve it. So basically then we are done actually. So this is the solution strategy. You have an equation for p to the power n, you factorize into linear factors, and then each one you can solve, because we know how to solve first order, first degree equations. Okay. Now see, for each of this equation, how will the solution look like? How did your solution look like earlier when we did this kind of equations? It will contain, your solution will contain, of course, x, y, and some constant of integration. So the solution will be like this. Say for any I, the solution will be some fi x, y, c, I. Just this is a symbolical representation, but we all know that the solution will contain x, y, and a constant of integration. So please see that, therefore, our final solution to the original equation, which is actually comprising of n such factors, the solution will be also the product of this n solutions, f1 xyc1, f2 xyc2, like this, fn xycn equal to 0. So basically you have a higher degree equation which is considered as a polynomial of degree n. You factorize into linear factors, solve each one of them, and the final solution is again the product of these factors. This is the entire philosophy. But yes, there is one more thing. As you see here, there is a word of caution. See, the solution we have written here, it has n constants, C1, C2, C3, Cn. But there is a but over here. We cannot do this because as per the definition of general solution, for a first order equation, the general solution can contain only one arbitrary constant. I hope all of you know that. A general solution of a nth order equation has n arbitrary constants. First order equation can contain only one arbitrary constant. So what we will do is, we will take all these constants to be equal. We will put a C for each of this Ci. So your final solution will be now written as f1xyc multiplied with f2xyc. It goes like this, fn xyc equal to 0. So this is the final general solution of your given nth degree equation. So this is the general theory for any nth degree equation. We will see problems now. Now, obviously, in your exam or as we will practice problems, we will not see very higher value of n. Usually, you will get n equal to 2. Maybe n equal to 3 cases possible, but mostly we will concentrate on equations where you have n equal to 2. So n equal to 2 will be actually not a really very difficult case, because you can imagine if you have p square, a polynomial of degree 2, that means it will be factorized into 2 factors only. So 2 linear equations you will solve and then finally write the answer. I hope I'm clear with the methods with all. Then I will go to problems.
Yes, ma'am.
Ma'am, can you please repeat the constant part? Ci. How can we write Ci by C?
See, we will be taking each constant as same. Like the first equation is giving me a constant C1. Second equation is giving us a answer a constant C2. But we will consider that all these constants are having the same value. That all this C1, C2, Cn, all we will take as C only. Okay. The reason is because when I'm writing the solution of the original equation, it is a first order equation. So first order equation can contain only one arbitrary constant. So basically, see, one arbitrary constants. The other constants we are fixing. Say the first one is C, and you can imagine like that if you have any doubt. Say for the one we are keeping at C, and the second, third, fourth, all this like C2, C3, C4, all this we are fixing to C. There is no harm, or rather we are not wrong, because as per theory we have one arbitrary constant. So C is one arbitrary constant. Rest of the constants we are just fixing it to C. Is that okay?
Yes, ma'am.
Okay. So now we come to problems. So the question is, solve the equation xyp square plus 3x square minus 2y square p minus 6xy equal to 0. So you can easily see that, first of all, observe the equation. There is a p. So we all know that p actually stands for dy dx, and it involves p square. That means we have actually a second degree equation. First order second degree equation. And now p square is there. So we are treating this as a polynomial of degree 2, or rather a quadratic equation in p. So we are treating this as a quadratic equation in p. So we're trying to get the solution. Now, there are many ways of factorizing, as you have learned in your school. You can try whatever you like. You can try to factorize by the middle factor method or whatever. Like here, we have simply used the Sridhar-Acharya rule, that if you have a quadratic equation, ap square plus bp plus c, I hope all of you know what are the roots, what are the p's, right? So here we have simply used that. Okay. So see that if we think this equation is of this general quadratic equation form, ap square plus bp plus c equal to 0. So that means this xy is my a, this 3x square minus 2y square is my b, and c is of course this minus 6xy, the whole thing. It is already written here. Okay. So therefore, for this quadratic equation, what are the values of p? I hope all of you remember what is the formula. It's minus b plus minus root over b square minus 4ac by 2a. So these two values have been written separately. So it's, you see, minus b. So minus 3x square minus 2y square. The first one is with the plus b square. You see, this is the b square minus 4. Your a is xy and c is minus 6xy. Denominator, you have 2a, so 2xy. And the other one is, of course, just a is plus is replaced by minus. So these are the two roots of this equation. If we think that this given equation is a quadratic equation in P, so we get these two roots for P. So now you need to simplify a little bit. Of course, I'm sure everybody can do that. So I will not show the calculations. I'll just write it simply. Please do check the calculations. The values will be 2y by x. The first one will be 2y by x, and the second one will be minus 3x by y, right? So therefore, we are getting the two roots, the two values of p as 2y by x and minus 3x by y. So that means we are getting actually two equations then. P equal to 2y by x, and the other one is p equal to minus 3x by y. So therefore, I can write this as p plus 3x by y. Okay, so basically these are the two factors, right? So now you can see that these are both of them are very simple equations to be solved because p stands for dy dx. If we look into the first one, so it is dy dx equal to 2y by x. So you can just simply solve by separating the variables. Dy by y is equal to 2 dx by x. So as I integrate, we will get log y equal to 2 log x plus a constant of integration. So now we can put the solution like this. Maybe instead of c1, if we write it in the logarithmic form, so suppose it's log k1. So therefore, we can write the solution as y equal to k1 x squared. 2 log x, of course, gives us x squared. So we can write the solution as y equal to k1 x squared, or if I take the k1 x squared on the left hand side, y minus k1 x squared equal to 0. So this is the solution of the first factor. Basically, your first factor is actually the values of p are this. So basically what is happening actually, the equation has been factorized like this. The first factor is p minus 2y by x, and the second factor is p plus 3x by y. So we have actually, so that actual equation has been really factorized like this. So the first one, this p minus 2y by x equal to 0, we have solved, and this is the solution. Now the second one is p plus 3xy equal to 0. This is again a very easy solution. You get it y dy plus 3x dx equal to 0. So as you integrate, of course, you are getting y square by 2 plus 3x square by 2. And this side you will write a constant of integration. Now just to get rid of this 2, it has been written as k2 by 2. It would not have harmed if you had written k2 also, but just to get rid of this 2, it has been written as k2 by 2. So the solution we can write as y square plus 3x square minus k2 equal to 0. So see that we have obtained the solution to the two first degree equations, two linear equations rather, and now the combined solution to the original equation, your original second degree equation, is just the product of these two solutions. So y minus k1 x squared plus y squared plus 3x squared minus k2 equal to 0. But now it's not over because we have still two constants. But as we have told that we should not write two constants, your solution should contain one arbitrary constant. So we will just use one now. And so the final solution will be given by y minus kx squared plus y squared plus 3x squared minus k equal to 0, which now represents the general solution to the original equation. So everybody is okay with this?
Can you explain the last
Yes,
step?
ma'am. Yes, ma'am.
I mean, you are okay with this two individual solutions?
Yes, ma'am.
Yes,
Okay.
ma'am. Yes, ma'am.
So please see, then finally the answer to the original equation is just you make the product of these two parts also in the solution also. So the first solution was 1 y minus k1 x square equal to 0, and the second one was this one. So you just combine these two as factors as the solution, which will give as the solution for your original equation. So I have just combined these two here. Okay. Now the only change, so just I have taken this one y minus k1 x square. This is 0 and this is 0. So of course their product will be also 0. So therefore y minus k1 x square multiplied with y square plus 3x square minus k2 equal to 0. Now the only change is that here you can see this solution contains two constants. But as per our definition of general solution, the general solution can contain only one arbitrary constants. So what we do is, as if we are taking both constants, we will give a same symbol, or rather you may think it like this if anybody is confused, that I am keeping one of the constants arbitrary and the k2 so suppose I just make, because it's 1, I'm just making it k, k1 is k. So in place of k, I'm writing k1, I'm writing k, y minus kx square. So k is an arbitrary constant. And the k2 I'm putting again as k. So k2 is no longer arbitrary, I'm putting k2 as k. So in that sense, finally, it's nothing but you don't need to put your head so much on that. Simply the final solution, just make one symbol for all the constants. So I have just put here y minus kx square plus y square plus 3x square minus k equal to 0.
Can I add something, madam?
Yes, sir. Please, sir. Yes, sir.
Because this is the right point to explain to them. All students, I cannot open my camera because it's creating problem. It's all right. But if you can hear me, it's fine.
Yes, sir. You're audible.
The equation is essentially first order, but higher degree. Now, first order means there is no derivative beyond dy dx. And we have learned that a first order equation has a general solution that can have only one arbitrary constant. So when you have the equation's solution as y minus k of 1 x square into y square plus 3x square minus k of 2, which is on the screen now. If you say that this is the general solution, somebody will take a gun and shoot you, because he or she will say, you are talking of first order equations and you are keeping two independent arbitrary constants. What the hell are you talking? You're not talking sense. So to avoid the threat of the gun, you change every K1, K2, K3 to K. Naming all your children as John instead of John, Edward, James, and something like that. To be in synchronous with the philosophy of the solutions of differential equations. That is a compulsion. There is no other choice. Is it clear? You have no other choice. Is it clear? At least one student.
Yes, sir.
Yes,
Okay.
sir.
Yes,
Yes, sir.
Yes, sir.
Okay, please carry on, madam.
Yes, sir. Okay, so I will now go on to the next problem, another example for this case solvable for P. So you see the equation P square minus P multiplied with e to the power x plus e to the power minus x plus 1 equal to 0. So you can see that this is again, it can be treated as a quadratic equation in P. In fact, this is a special one, you can say. There is no y involving, but anyway, that does not harm. We have dy dx and x over here. So we can treat this as a quadratic equation in P. So once again, we will go with the same philosophy. We will try to factorize. Of course, it will get factorized into two factors. So now here we have just shown a different way of factorization, which again all of you know. Instead of solving with the formula of the quadratic equation, getting the roots, we have just tried to factorize using the middle term factoring process. So for this, just have a note that this is e to the power x plus e to the power minus x plus 1. And see that if I have the product of e to the power x and e to the power minus x, that gives me a 1. So actually this equation we can think of as p square minus p multiplied with e to the power x plus e to the power minus x plus, in place of 1, it's nothing wrong if we write this because they are both same, e to the power x into e to the power minus x. So now you can see we can easily factorize this. If we collect, if from the first two terms, let me write, if I take p common from the first two terms, you see it will give me p minus, if I take p common, I will get p minus e to the power x minus, you see next term would have been minus p e to the power minus x, and here you have this e to the power x e to the power minus x. So now if I take a e to the power minus x common from the next two terms, what will I get? I will be left with this p here, and here again I will be, because I have already taken a minus common, so I can write this as p minus e to the power x, right? So therefore now you can easily relate to this line. So basically then we are getting the two factors, p minus e to the power x multiplied with p minus e to the power minus x equal to 0. So we have factorized this using the middle term factoring process. Now which process you will use for factorizing, that's up to you. So we have just tried to put up different ways. So please see that then, therefore we have two linear factors now. One is p minus e to the power x equal to 0, and the other is p minus e to the power minus x equal to 0. So therefore they need to be solved one by one. So the first one, p minus e to the power x equal to 0, obviously this is dy dx equal to e to the power x, and it's one of the easiest equation to solve, because as you will integrate e to the power x, you will get e to the power x itself. So your solution here is y is equal to e to the power x plus c1, our constant of integration. So it's y minus e to the power x minus c1 equal to 0. So this is the solution to your first equation. The second equation we can easily solve again in the same line, only a minus will be added. So this is your second equation, p minus e to the power minus x equal to 0. So this gives me dy dx equal to e to the power minus x. So as you now integrate this e to the power minus x, I will get a minus e to the power minus x and plus the constant of integration. So this gives me now y plus e to the power minus x minus c2 equal to 0. So we have two solutions for the two linear equations. So the combined one will now give you the solution to your original equation. And as we are combining, see that now we have not stated much. We have directly taken the constant as c. So the first solution was y minus e to the power x minus c1. I'm just written it as c. And the second one, y plus e to the power x minus c equal to 0. So simply you get the solutions and just combine them to get the final solution. Only thing, caution, you have to remember that don't write c1, c2, make it a simple one. That's it. So therefore, once again, let me summarize the solution strategy for this kind of problems which we are telling the type 1 solvable for p. We are visualizing the equation as a polynomial in p. The degree of the polynomial decides that how many factors you will get, and mostly, as you have seen, we are taking only quadratic equations. So in your case, mostly it will have two linear factors. Each factor is a linear equation which you know how to solve. So you solve each of them and simply then again combine them. That's it. So I hope this is okay. Anybody, any doubt over here?
Okay, ma'am.
Yeah.
Ma'am,
Yes, please.
ma'am, after combining, there is no need to solve.
So what will you solve? This is the solution, isn't it? This is the solution to the first part, and this is the solution to the second part. So this combination, see, actually what is happening, if you come over here, just a moment. Yes, your original equation, this is given with this. The original equation, this is equivalent to this. P minus e to the power x multiplied with p minus e to the power minus x equal to 0. So now see, when a dot b is 0, either a is 0 or b is 0, any one is going to happen. So if this one happens, you get that solution. If this one happens, you get the other solution. So finally, you just combine, and that is going to give the solution of the final equation. Okay.
Okay, ma'am.
Yeah. Sir, any comment, Legacy sir? Or shall I proceed?
No, I want to comment like
Yeah.
this, and it is for all the students. Please understand very carefully which one is the differential equation that you are going to solve. That is generally given to you. Now, the last gentleman who asked this question, that after making both the constants C, do we have to solve the equation further? There is no question. You see what you have on the screen, y minus e to the power of x minus c into y plus e to the power of minus x minus c is equal to 0. Each of them is a solution, hence their product, because the right hand side is equal to 0, their product is also a solution. And this is the general solution because it contains just one arbitrary constant. I hope it is clear. So please try to understand the meaning of or the difference in meaning between an equation and its solution. Supposing I just give you a very simple one, and all of you, I think, should have a piece of paper to write on. Supposing you have dy dx is equal to e to the power of x. Is this a differential equation? Yes or no?
Yes, sir.
So
Yes,
what is the order? Dy dx order is
Sir, one.
So first
One.
order.
first
order.
order.
First order.
So if dy dx is equal to e to the power of x, do you agree that y is equal to e to the power of x plus c is
Yes,
a
sir.
Yes, sir.
solution?
Yes, sir.
How many constants? We don't have to write
One.
C1, C2,
One
C3.
constant.
One constant.
One constant because it is of the first order. So appreciate this part very carefully. And you say in the examination, when you're writing a note, you have to explain this very carefully. Supposing it is a 5-mark or 10-mark question. Just changing all the C1, C2, C3 to C without a comment, justifying the philosophy of turning all the constants into one C. Without that comment, maybe brief, you don't earn full credit because it gives the examiner the idea that you are not yourself very clear about the philosophy of solutions. Am I clear? So please go through this, differential equation part very slowly and try to digest every bit. Thank you. Sorry? Somebody's mic is unmuted, I don't know.
Maybe just muted.
Madam, please carry on.
Okay. Yeah, so just one more comment on this line. As students, yes, definitely you should be very much careful, and you should be very much clear about what is a differential equation and what is its solution. And as I told in all classes, I just wrote with examples. So differential equation means an equation which contains a derivative or differential. So as sir told, yes, this is a differential equation. And what is a solution to it? Solution means it's the function of x, it's y, which satisfies the equation. So your solution contains y as a function of x. So solution contains y, x, and a constant of integration. This is what was written in our first slide also, that the solution is of the form of some function of x, y, and c. And when we wrote the differential equation, you remember, it is a function of x, y, dy, dx. So if you understand this clearly, there should not be any confusion. So this is the differential equation and this is the solution to it. And for this higher degree equation, simply we are combining the solutions as obtained from the first degree equations, right? Okay, so now we will continue. Now see, I have another question on this type, but now I think I will skip this. The PPT will be shared. You try to understand on your own because the philosophy is same and it's will be in the same line as we explained example number 1 and 2. But better now I will go to the other types because I have to do type 2 and type 3 situations also. So please try to do it on your own, but everything is done. If you have understood the first 2 problems, surely you will understand the 3 also. So now this is a, yes, please.
Ma'am, I have a question. How can we determine the trial solution of any equation differential? As I have seen recently, the equation you have just
See, here it is written, but it won't be. I mean, you can. Yes, I think you are talking about this one.
yes, ma'am. Yes.
See, this was just a hint that looking into this dy dx, this form of the equation that dy dx equal to x by y can be, but you need not. I mean, I think at this point here you need not concentrate on this. You can just skip this also. Just try to write. Okay, anyway, let me just then start it. Then we will go. You see, dy dx is p. Dx dy, if dy dx is p, dx dy will be written as 1 by p. So the equation is p minus 1 by p equal to this x by y minus y by x. So it's x square minus y square by xy. So this is the equation, or if we just simplify this a little bit, p square minus 1 by p equal to this, or rather now if I do it here, take the xy on this side. So p square minus xy equal to x square minus y square equal to p. So ultimately, if you just rewrite the equation, writing dy dx as p and dx dy as 1 by p, you will simply, as you can see, it is again a quadratic equation in p. So as you get a quadratic equation, just follow either the process explained in 1 or 2, any one of the ways to factorize. You can try the middle term factorization process, or you can simply try to get the roots and you will get the answer. So I think better don't, I mean, this is just a suggestion here because this dy dx equal to like dy dx equal to x by y. So that is just a suggestion, not that everywhere it can work, that can be a possible factor. That's it. But need not concentrate much on that. Simply try to write this equation in the proper form as a quadratic equation in P and then get the roots. That's it. In fact, but yes, that was a hunch as it was already told. But ultimately, when you get the roots, you see the one of the equation is this one only, dy dx equal to x by y. That is that only comes as one of the factors. Okay.
Yes, ma'am.
So rest I'm not explaining. Now these things you can, I mean, you can do the factorization and you can solve these equations are too easy. So you can do it. So now I will go for equation solvable for y. So now this class of equations, so once again, we are in the same category as first order higher degree equations. That means my equation can contain x, y, and p. But now some equations may be given in this form, or rather it will be good enough to put it in this form that you keep y on one side and x and p on the other side. That means we, as if we write y as a function of xp. You remember that our equation will be containing 3 variables. We are thinking of it as a function of x, y, and p. Now, some situations it's easier to work on where we keep y on one side. Some may be directly given, or some maybe you have to adjust y on one side and xp on the other side. Okay. Now, how writing an equation in this form can help? See that what we will do is we will differentiate this equation with respect to x. This equation, suppose that we have written our given equation in the form y as a function of xp. Now we will differentiate both sides with respect to x. So left hand side, if I differentiate, it is dy dx. That is nothing but our p. What are the things can come in our right hand side? The right hand side is containing xp as variables. So definitely x and p will be there. And now if as I'm differentiating the equation with respect to x, so dp dx, this is also going to come. So therefore, after differentiating this equation with respect to x, what are the things we can have in our equation? The left hand side is directly p. The right hand side can contain, of course, xp as well as dp dx, because we have differentiated this as a with respect to x. And please assume that, I mean, understand that we are taking p as a variable, so it is giving us dp dx. Now see, it will be a first order ODE. Now, please, another thing to be noted, once we do this, y is gone. This equation, the equation number 4, will not contain any y term now, because we have different, this was the only y term. Y here, it was the only y term. Right hand side contained only x and p. Left hand side contained a y, and as we differentiated, we got a p. So this equation 4 does not contain any y term, right? So therefore, this equation 4 is actually containing x, p, and dp dx. And please see that this will be a first order equation in p and x. Obviously, because I have only first order derivative dp dx. Okay. In fact, not only first order.
Ma'am,
I should say, yes.
just one thing, but P itself is dpdx is itself dp is itself dy dx. So if we consider dpdx, then it can be d2y by dx. So
Yes, it is. But at the moment, we are not thinking of that. We are thinking p as just a variable. At this moment, we have to forget that p is dy dx. P
Okay,
is
ma'am.
just a variable for us. Okay. So this is a first order equation in p and x. Not only a first order, I should say this is a first order and it will become a first order and first degree also, because definitely I'm not going to get any dp dx whole square or anything like that. When I'm differentiating, I will just get only dp dx. I cannot get any dp dx whole square or something like this. So therefore, actually, this will be not only a first order, actually this will be a first order, first degree equation. And then we are going to solve this as usual, as we know how to solve. Okay, so the solution, now see, I am having an equation in x and p. So the solution will contain what? The solution will contain again x, p, and a constant of integration. See that when you had an equation with x, y, the variables x, y, and a derivative like dy dx, your solution contains what? Y as a function of x. So a solution contains y, x, and a constant of integration. Here your variables are x and p. Basically, when I'm writing dp dx, that means p, we are taking p as the dependent variable, x as the independent variable. So therefore, this the solution will contain xp and a constant of integration, right? So your solution to equation 4 will look like this. Now, the next task you have to eliminate this. Now, for the solution to the original equation, we will expect the solution containing x, y, and c. So what is expected now, that we should eliminate this p from this equation 5 and the original equation 3. It is expected that we will try to eliminate this p from the original equation 3 and this. If we can do this, if we can eliminate p, what the things it will contain now? What are the things left? H
yx.
and c. So the usual expected form of a solution will be obtained. Okay. Now we will talk about this elimination process with examples. They are again a little there are some buts over there, but theoretically it is like this. So once again, I explain once more that suppose that your first order higher degree equation, I am able to write as y as a function of xp. Then we will differentiate with respect to x. So what will happen, that y will go away and I will get an equation in x and p. First order equation in x and p, which we know how to solve. We will solve. The solution will contain a p because our variable now was p, but this p has to be eliminated using the original equation, and then you can get the final solution. But yes, that elimination might be a complicated one sometimes that we will discuss with the problems. Okay. Okay. Now, this is example, and obviously this is very clearly, it is of the form of y equal to some function of xp. It is already directly given in this form, y equal to function of xp. So y equal to 2px minus p square, right hand side contains x and p. So as I explained, we will differentiate with respect to x. So left hand side is dy dx, right hand side, what is happening, you see, 2, if I differentiate this p, I will get 2 dp dx and the x, that means this first term. Now again, if I differentiate the x, I will just get 2p, and when I differentiate this p square minus 2p dp dx. So
Madam,
this is
can I disturb for a second?
yes, please.
I'm leaving for about maximum 2 to 5 minutes.
Okay, sir, no problem.
I think the gas wala has come. Okay.
Okay, no problem. No issue.
I'll just come back.
Yeah. So please see, this is the equation what I'm getting after differentiating with respect to x. Now, as we all know, left hand side dy dx is just a p, and the right hand side here I have kept same, not yet changed. Now we try to combine the entire thing, take the p on the right hand side, and also see here I have a dp dx term and here I have a dp dx term. So this two can be combined. So combining this two, I can write it is 2x minus 2p dp dx, right? And here I had a 2p, and when the p from the left hand side goes, 2p minus p, it gives me a p. So my equation becomes now 2x minus 2p dp dx plus p equal to 0. So that is what I told in the theory. You see that after differentiating, I will get an equation purely in x and p. First order differential equation, as you can see, in x and p. So we will try to solve it because we know many solution methods for solving first order equations like this. Okay, so now see that it will be easier. I mean, we won't be able to put it in a linear form as dp dx, but if we revert the roles of x and p, as this kind of things we have done for linear equations earlier also. So what has been done, if I take, please see, if I want to do it like this, it is dp dx plus p by 2x minus 2p. So that will create a problem. I won't be able to work much with it. Instead, what we are doing, we are taking the dx dp on this side. So it's p dx dp plus 2 times x minus p equal to 0. So of course, you can see that this is basically a linear equation in p. And if I now divide by p, it is dx dp plus 2x by p minus 2p by p. So that will give me a 2, and I take it on the right side. So it is dx dp plus 2x by p equal to 2. And I hope everybody can see that this is a linear equation in x,
Yes,
where
ma'am.
x is the dependent variable, y is the independent variable. You know, so you to solve it, what is the integrating factor? Everyone knows. What will be the integrating factor? You see here, actually the coefficient of x is 2 by p, isn't it? The coefficient of x is 2 by p. So therefore, your
e to the power 2 by p dp.
right, it is e to the power integral 2 by p dp. So it's 2 log p, and finally it comes out to be p squared. So this is very standard procedure which all of you know how to solve. So Next, of course, we will multiply by this integrating factor. So once I multiply by the integrating factor, this is p squared dx dp plus 2xp equal to 2p squared, just usual multiplication. And again, you know, this I have told you in the classes several times, that the left hand side will always emerge as ddp of, what is that? It's the dependent variable you have to take, x, and this integrating factor, ddp of, that will emerge in every linear equation. I have told you many times in the classes, those who had attended my classes rather, it always happens that because after multiplying with the integrating factor, the equation becomes exact, we would be able to write it as d of something. So it will always happen like this, that here it is ddp, my variable is p, so it's ddp. And what is that? X is the dependent variable multiplied with the integrating factor. And if you want a check, please do it. You should do a check. If I differentiate x, I will get one term dx dp p squared, that is the first one. And I differentiate p squared, then I will get 2xp. So obviously this matches with this ddp of xp squared. And right hand side is 2p squared. What is the next step? Obviously, next step is you have to integrate. So if I integrate xp squared, the left hand side gives me xp squared. The right hand side 2p squared, if you integrate, of course, you get 2p cubed by 3 plus a constant of integration. So, maybe I divide by p squared. So we can write the solution as x equal to 2p by 3 plus c p to the power minus 2. So if you just come back one for a moment, yeah, as you see, as we told that after differentiating, we are getting this equation, we are solving, I will get a solution in x, p and c. Please see that that is where we are now, that we have got a solution in x, p and c. It is okay up to this? Yes.
While solving linear equations, can we directly write the solution in integral form and then integrate it?
Yes. If you remember the formula for the linear equation, there is a formula. If you want to use this and you want to write the solution, you can do that. No harm. Okay. Fine. Okay, so whichever you do this process or you use the formula, this is the solution you're going to get. So this is the solution as involving x, p and c. Now next, what we told, actually our solution should not contain p. P is some extra parameter basically. P is dy dx, but the solution should not contain a p. So what we are supposed to do is, we are supposed to eliminate this p. And how will you do that? As we told in the explanation slide, that we will use the original equation to eliminate this p. Now see, what was our original equation? Y equal to 2px minus p squared. Now see the problem. It's very difficult. As I told you already that there is a caution over there, this eliminating p, that may not be a very easy task. Eliminating p is not always an easy task, because if I have to really eliminate p, I have to get an expression from, please understand, then I have to get an expression for p in terms of x and c, and then I have to put it there so that p totally gets eliminated. But that is a very difficult task. I really won't be able to do that because I have a p and I have a 1 by p squared. So get the expression for p is very difficult, and this is going to happen in many problems. So how do you resolve the problem? What we do is, now instead of eliminating p, I just take the value, I just, one way you can see that I am eliminating x from the first equation, that I put the value of x like this in the first equation. What was our original equation? Y equal to 2px minus p squared. So in place of x, 2px, I am writing this 2p by 3 plus cp minus 2. Okay. Now see, we have a set of equations as written as a and b. where x is given like this, 2p by 3 plus c p minus 2, and y is also given like this. So basically you see x is given in terms of p and the constant of integration, and y is also given as in terms of p and the constant of integration. And what we will say that this pair of equations, this gives us our solution considering p as a parameter. Now you might be confused at that point that I'm not getting the solution in terms of x, y, and z. The thing is that we are supposed to, theoretically, we are supposed to get the solution as x, y, and z, but we are not being able to eliminate the p. So in that case, we write the solution as a pair, x in terms of p and c, and y in terms of p and c. Now, how this is justified? See that, please remember, all of you know this. I mean, all of you have heard of parametric equations. See, if it's a parabola y square equal to 4ax, the parametric equations are x equal to 80 square and y equal to 280. So we can always write a Cartesian equation in place of x and y. We can introduce a parameter and write in terms of a parameter, right? Even a circle, what is the parametric equations for a circle? If I give you a circle, x square plus y square equal to r square, what will be the parametric equations? Anybody?
X equal to r
X,
cos
r
theta, y
cos
equal to
theta,
r
r
cos
sin
theta.
theta.
y equal to r square cos theta.
Right. X equal to r cos theta, y equal to r sin theta. So theta is the parameter, right? So it is allowed that we write a solution instead of directly involving the two variables, x and y. It is allowed that we are writing x and y in terms of a parameter. So here also the logic is that because I'm not being able to eliminate the p directly, we treat that p as a parameter and we have the solution in terms of the parameter. So x and y, this is actually giving us parameterized solution. Okay.
May I add something, madam?
Yeah, please, please. Absolutely, sir.
Adding means I am asking the students, anybody can answer. The parametric equation part of a circle, all of you said x is equal to a cos theta, y is equal to a sin theta, and that is it. Now, is this answer complete? Anybody can say yes or no? Because I think it is incomplete. So can
Sir,
anybody, yeah,
may I
tell me.
answer?
Yeah, please do.
So will it be r square cos square theta plus r square sin
No,
square theta equals
no. That is, the different way of showing the same nose.
So,
Bolo.
The
sir, will
theta
it be
can
x
be
equal
0
to
to
x naught by r
360
cos
One
theta?
by one.
Sir, will it be x equals to x naught plus r cos theta, y equals to y naught plus r sin theta, where x naught and y naught are the coordinates of the center?
No, not at all. I mean, you're partly right, but there is something lacking in your answer. One more
Where r
student
is the
will-
radius of the circle.
that is implied. Acha, now I'll tell you the actual answer by asking a question. What is the domain of theta?
0 to 360 degree.
Yes, you must write
Yeah.
theta less than equal to 0, greater than equal to 0, less than equal to 2 pi. But you cannot put equal to on the 2 pi if you put the equal to on the 0. Otherwise, one point will be repeated twice. So parameterization, you must also remember very carefully what is the domain of the parameter. Madam, please carry on.
Yes, sir.
Ma'am,
Okay.
just one thing.
Yeah.
Can you just repeat once more? How are you replacing the combining the two equations?
Yeah, just one moment. Just a moment. Yeah. Just a moment. Let me come to the slideshow mode again. Yeah. What again? Repeat the question. How I'm combining?
Yes,
See,
ma'am.
it's not that there is the problem. We are not really able to eliminate the P and write it in the form of, like, as you can in a parabola or a circle, you can eliminate and write it. But here it is difficult. It's not that totally impossible, but it's difficult to eliminate the P. So the thing is that this two, keeping the solution in this x equal to this 2p by 3, whatever is this A and B, the combined one is representing our solution in the parametric form. That is the philosophy. I'm not being able to write our solution should contain x, y, and c, but I'm not being able to do that. So instead, I'm writing the solution in the parametric form, where this both A and B represents the solution to the curve, whatever it's representing, in the parametric form. That's it. Okay.
Yes,
So
ma'am.
you are not going to do anything further. You are just going to write. Finally, you will say that this A and B together makes the general solution. You see, here it's written. I mean, actually, I have not here come up to this. So finally, you see, it's the standard way to represent the answer to this problem is the P eliminant between the following pair of parametric equations gives the general solution, with P being the parameter. So with the idea that if I can eliminate the P, that gives us the general solution. But yes, we are showing that we are presenting the solution without doing the elimination. But with the philosophy, yes, if we eliminate, we will get a relation between x, y, and c, which will represent by general solution. So the final answer should be written like this. Is it okay now?
Yes, ma'am. Ma'am, just to clarify one thing, the derivative of y with respect to x, which was actually p, now this p has been converted into a parameter.
Yeah. This is when we are solving, we are treating this as a parameter. Yeah. Yes. Okay. Okay. So there is one more question in line. Y equal to 2px plus p4x square. So once again, we can easily see that it is in the form of y equal to function of xp. So this basically, these equations are easily identifiable. You can easily, I mean, usually you people will have a question that, yes, given us higher degree equation, how will you understand that which method to follow? But you see, question number 4, 5, these are very easily identifiable, that it is in the form of y equal to function of xp, right? So we will start straight away differentiating with respect to x. So dy dx, I get on the left hand side, which will be obviously p. The right hand side is 2p plus 2x dp dx. And now I have to differentiate this p4x square. So this is, if I differentiate the x square first, it's p4 2x. Plus when I differentiate p4, it's 4p cube x square dp dx, right? So here you can see that this p, this dy dx is obviously a p. When you will take this p on the right hand side, I will get 2p minus p, so I will get this p. Next, I have this 2x dp dx. And from these two terms, we have taken this 2p cube x common. So I'm getting again p plus 2x dp dx. So you can see easily that this is getting factorized as this p plus 2x dp dx with 1 plus 2p cube x. So you see that this is easily getting factorized like this. Okay. Now, of course, when I have two factors, there are always two possibilities. Either the first factor is 0 or the second factor is 0. But note one thing, if we look into this second factor, is it something feasible? 1 plus 2p cube x equal to 0. Right? This second one. I'm talking first about the second factor, 1 plus 2p cube x equal to 0. Now, this actually means, you see, 2p cube x equal to minus 1, or rather p cube will be minus 1 by 2x. and therefore p is going to be minus 1 by 2x to the power 1/3. So I have minus under a radical sign to the power 1/3. So definitely this is leading to some imaginary value. And physically this is not possible because we know that p is dy dx. So this value of p is not physically possible. So therefore, here we although had two possibilities that either p plus 2x dp dx is 0 or 1 plus 2p cube x equal to 0, but physically the second one is not possible. So definitely then we have to work only with this factor p plus 2x dp dx equal to 0. So this is what you have to take a little bit care. Okay. Otherwise, the process is same as we followed. But one thing is that now here we are getting two factors. One factor does not work because that does not give a physically possible case. The other one we have to work on. And of course, the other one, you can easily see it's a very easy equation. It's easily solvable. We can separate the variables easily. So it is p equal to minus 2x dp dx, or rather we can have separate the variables. So it is minus 2 dp by p, and the other side is dx by x. So you solve it, you get, of course, we can take all on the same side, then 2 log p plus log x. The constant of integration, you can write as c, but it's better to write it as log c, then it makes the life easier. So you get p square x equal to c square. Now see, here this is an example, like last problem, we were unable to eliminate the p, and so we wrote the solution, final solution in the parametric form. But this is a case you will see that here it's not the case. Yes? Anybody?
From where c square is coming, it is log c.
It is printing mistake.
Yeah, so that in that case you can think of, yeah, that's right. But that means as if I'm taking the constant itself as log c squared, just to keep it in a plausible form, basically in a better form. Otherwise, if I keep it as c, here again I have to take a root c. That is it. You're right. Thank you for noticing that. But it has been just because it's a constant, I write as c or c squared. It has been just written to make the things look better. That's it, I can say.
Okay, thank you.
Thanks for noticing that. Yeah. So therefore, this is p square x equal to c square, or rather p square equal to c square by x. So please see, as what I was pointing out, that this is actually, now last case you saw what we got, or rather for this equation, when I will get a solution, I will get a solution in terms of x, p and c. So last case we were not being able to write p in terms of x. And that is why we wrote the final solution in a parametric form. But here we can get the value of p. This is a easier one. We can get the value of p easily because p square equal to c square by x. So therefore, of course, I can write p equal to c plus minus c by root x. Or rather, basically, this is giving me, therefore, or it's written like this. It's the same thing. So finally, it is giving me two values of p. One thing you can see now, it is giving me two values of p. One is p equal to c by root x, and the other one is p equal to minus c by root x. So now I can solve this to get the value of p, right? So please see, or rather it has been written into two factors. It means the same thing. So the first part, p plus c by root x equal to 0. So as p is dy dx, you see now that I can easily integrate this and I get an answer for y. So it's dy equal to minus c dx by root x. Obviously, you can integrate this. This will be your answer, y equal to minus c integral x to the power minus half dx. So as you integrate this, it will give you minus c 2 root x, right? Now you may say, yes, there should have been another constant of integration as I integrate. But as we all know, by now, I hope we have understood that we can have only one arbitrary constant. So we will not add any further arbitrary constants over here. So the solution is y plus 2c root x equal to 0. And similarly, I hope you can easily understand it's just a matter of sign. The other one will give you y minus 2c x root x equal to 0. So finally, we get the solution, the general solution as desired, not in the parametric form in that p eliminant form, but it is, we can finally write the solution as y plus 2c root x, y minus 2c root x equal to 0. Okay. So wherever possible, actually the simpler ones, wherever possible, we should try to really eliminate p and get the solution in the desired form. But wherever it's not possible, where you cannot eliminate, there only we keep the solution in the parametric form. So is this okay?
Yes,
Any doubts over here? Okay, so
Yes, ma'am.
fine.
Ma'am.
So next, again, there is one more problem, but now again, I will skip this for you. Two I have explained. So the third one I will skip for this for you, because now I will proceed to the third situation. Okay, one thing before just I can see, show you here that this solution is again given in the eliminant form. That means the parametric form as x and y. So possibly it is not, not possibly, you can see your x is 2 tan inverse p minus 1 by p plus c. So it is not really possible to solve for p. The way we did in the previous problem, we could solve for p and therefore we could get the solution in terms of y. But here, whenever it's not possible, we will keep the solution as this pair. Okay. So please go through this. Now let us come to the third case, equation solvable for x. So this is just sort of, you can say, a reverse of the type 2. The type 2 was you're writing y as a function of xp. And now here you are writing x as a function of y. So it depends on the your question, of course. Sometimes that is easier to do, or that is possible, and sometimes this is easier or rather possible. Not that every equation I would be able to put it as a type 2 or type 3. It will depend on your question. But if you have understood the type 2 solvable for y, the process is quite similar. Just the roles of x and y are getting interchanged, basically, I can say.
So, madam,
now
I just had a problem, small question. Is
Yeah.
Nritik there in the meeting?
Yes, sir.
Asha, madam, we
Yes.
have to share an attendance link because many students are leaving.
Yes, absolutely.
Attendance link, and after 5 minutes, please share an attendance link.
Okay.
Take Asha.
Okay, so the type 3 is now x is represented as a function of y and p. So now you can see, you can guess, previously it was y and we differentiated with respect to x. Now on the left hand side, you have a x. So we differentiate with respect to y. So left hand side, it will give me dx dy. And as we already told, dx dy we will be writing as 1 by p. And what will be the right hand side as you are differentiating? Please see, right hand side contains y and p. So of course, after differentiating, we may contain y and p, as well as we are differentiating with y, we will also get an additional dp dy. So the equation will now take a form like this: 1 by p equal to function of y, p, and dp dy. So obviously, what are the things then you are having finally in the equation? It's p, y, and dp dy. So there is no x now. Please remember that x is gone away, has gone away. It's not there. Earlier type 2, y had gone away when we differentiated with x. And now when we differentiate with y, x has gone away. So it is now a first order equation in p, y, p and y. Basically, these are the variables. And of course, you're having the derivative dp dy. So as I told you, the situation is very similar. You can just think of as if the roles of x and y are has got interchanged. Rest are all the same. So now we will solve this equation 9, this one, the ODE, first order ODE in P and Y. So your solution will contain what? P, Y, and C, right? So once again, if you can eliminate P, now the elimination has to be done, of course, between this equation, the solution, and the original equation. If you can really eliminate P, you get your general solution in terms of X, Y, and C. And if you are unable to eliminate P, you will keep the solution in the parametric form with a pair of equations using X and Y. So I think it's the very similar as type 2. Okay, I think it's better that we move for problems. So here there is a equation, tan inverse P is x minus P by 1 plus P square. Okay, it's not readily in the form of x equal to function of Py, but yes, we can do it. I keep x on the left hand side. So I recast this equation in the form x equal to tan inverse P plus P by 1 plus P square. So basically, even this is still spatial that I don't have a y also. So x has been just a function of P. But we will proceed in the same, in the same way as explained. Whether y is there or not does not harm. So we will differentiate this equation now with what? Of course, with respect to y. So as I differentiate with respect to y, it's dx dy on the left hand side. Tan inverse P, we all know it's 1 by 1 plus P square, and I would have a dp dy. And now as I will differentiate P by 1 plus P square, so what is that? Obviously, we'll use the u by v rule. So denominator is 1 plus P square whole square. The numerator, if you differentiate P, you will get a 1. So 1 multiplied with this denominator, 1 plus P square, minus P multiplied with the derivative of the denominator, that is 2P. And definitely you get a dp dy. Okay, so now next line, dx dy, we will just replace this with 1 by P. And the right hand side needs a little bit of simplification. If you simplify, you will see, I hope all of you can do that. You just, dp dy, you can see that you can take common from both the terms, isn't it? dp dy is coming common. And then whatever the coefficients of dp dy you have, you simplify and you will get, I'm not explaining that, you can do that. It will be 2 by 1 plus P square whole square. Okay. So then we have, this is then a first order equation in P and Y. So, and this is again an easy one because basically you can just solve by separation of variables. I take the y on this side and the p on this side. So it's dy equal to 2p by 1 plus p square whole square dp. So this is your old method of separation of variables, which you know. Okay, so I have just skipped the steps here. I hope everybody can do this integration. You should be able to do it, right? So you integrate this side, obviously you will get a y, and the right side you integrate, you will get this along with the constant of integration. So this is going to be your answer. So only one thing, if you look into the type 2 case, there you were actually differentiating with respect to x, and then you were solving for x, and the original equation was for y. Here it is the reverse. When you are solving, you are getting y, and your original equation is with respect to x. So when you pair this up, this gives you the parametrized solution, x equal to tan inverse p plus p by 1 plus p square. This is the original equation, mind it, and this is the one you have solved. Okay, so this is very similar as type 2 case, only the roles of x and y have been reversed. Is this case okay with all?
Can you please explain the last part?
Yes, sir. Can you just explain it?
Can you show the previous slide?
Okay, I'm going. Maybe I will just see this. Let me repeat only. So this is your equation. I have rewritten it as x as a function of py, but especially we don't have a y. So it has simply come in the form of x as a function of p. But it is the type 3. It's only a still special case that y is not appearing directly. So I have written this as x equal to tan inverse p plus p by 1 plus p square. So what is the solution procedure for this type 3? When you write equation as x as function of py, you differentiate with respect to y. So we have done this. So left hand side is dx dy, which eventually we will write dx dy is 1 by p. And the right hand side I have differentiated with respect to y. So I had explained this differentiation. I hope that is okay. And when you differentiate, of course, you are going to get this dp dy. Tan inverse p is 1 by 1 plus p square dp dy. Here also you are differentiating this term and then you get a dp dy. So next line you see, we have just simplified it. Next line is left hand side 1 by p. And the right side, I'm just combining these two terms. dp dy is coming common from both the things, this dp dy. And now if I combine the coefficients, you will easily see that this is 1 plus, actually, if as some of you asked, let me explain. So what you are doing, if I'm combining this two, if I'm taking the denominator as 1 plus p square whole square, and this side as I had 1 plus p square, so numerator, what you're going to get? You will get a 1 plus p square, isn't it? Plus, again, you see you have a 1 plus p square. So you will get 1 plus p square minus 2p square. So 2p square, left hand side, right hand side, it is cancelling. So ultimately you are getting this. So ultimately this big thing gets simplified as 2 by 1 plus p square whole square dp dy. Okay. So we can see now this is obviously first order differential equation in the two variables p and y. We try to solve that. How will you solve that? We can easily see that I may take this p on the right hand side. So basically I can make this as 2p dp this, and I will take dy on this side. So your equation is going to be dy equal to 2p dp by 1 plus p square whole square. Okay. So one side you have y fully, one side you have p fully. So definitely you will solve by method. This is what we are using basically then the method of separation of variables. So basically once we have separated the variables, we simply integrate directly, isn't it? So if I integrate, the left hand side will give me y. The right hand side, of course, you have to integrate. How will you integrate? Anyone? 2p dp by 1 plus p square whole square. How will you?
1 plus p square we can consider that p, then it will be
right. Absolutely. So
t square.
You will make a substitution. 1 plus p square equal to say z or anything you can write. So once you do it, you will get the answer. And there is a finally the answer is coming as y equal to c minus 1 plus p square. So please see that we have obtained the solution for this equation 14, right? Sorry, extremely sorry. This is not the equation solution for 14. This is the equation for this one. I have not given a name for this. This is the equation for this solution for this equation, right? So where we are, which was a differential equation in p and y, and we have got it. Now, this is not directly the solution for our original equation because here the p is appearing. So what we told earlier, that this means that we need to eliminate the p. From where will you eliminate the p? You have to eliminate the p from the given equation. We have to eliminate the p from this equation. So if you can eliminate the p totally and get your solution in terms of x, y, c, that is fine. But otherwise, when the things are complicated, we cast the solution as if thinking that p is a parameter So we have the solution in the parametric form. So we have written this x and this is as y. Okay.
Okay, ma'am.
Yeah. So it's fine that we keep the solution in this parametric form, right? So it's already 12:30. So sir, shall I stop or do I?
Yeah, it is better to stop for today.
Better to stop.
You have a wonderful lecture.
Unless somebody has any very
Most
specific
important,
question.
Yes, if
link
you
is
have
also
any
given.
parents, students, you can do. And there is what I can add is, yes, there is one more example over here for this case. So that you can, if you have understood the previous example, you can, it's all detailed steps are shown. So you can see just this equation. Now, okay, one comment I would like to make, that maybe you may be tempted to think it as y equal to fxp, but because you see y on the left hand side, but that does not work because you can see here also there is a y. This is just a caution for all, that maybe looking into this, as you can see a y on the left hand side, you hurry up to think that this is of the form y equal to fxp. No, it is not in the form of y equal to fxp, because right hand side you have a y. Okay. So you won't be able to cast this in the form of y equal to fxp, but instead we can cast it in the form x equal to function of yp, right? So you see here, we have taken the x on the left hand side, and now I could write this as x as a function of y. So please look into the form carefully. Although sometimes suddenly it gives us a look, but there is a y hidden over here. So this form type 2 will not work. You have to work with the type 3, x as a function of yp. Now, if you have understood, the process is same. You differentiate with respect to y. So you will get an equation in. So once you differentiate with respect to y, actually x will go away because dx dy will be replaced by p. So you will get an equation in p and y. So you will solve the equation, and then finally you can get the answer. But here again, this is a case, I'm not going into all the steps, but this is a case where you can actually eliminate the p. You can see that final solution is given in terms of x, y, and z. So one example is there where you are not being able to eliminate. You're keeping the solution in the parametric form. The other example is where you can actually eliminate the p. You can get p and put the solution in the desired form of the general solution containing x, y, and z. So I hope that is okay. It clarifies this doubt. Anybody else?
Yes,
Anything
ma'am.
asking?
Ma'am, can the attendance link be resent once again?
Yes, I am also not
Okay.
in the chat section.
Again, it is sent. Send it again, attendance link. Why is that telling so? Just a minute, beta. Mr. Mithik Ghosh is again sending the attendance link.
Okay, now just one last comment for students, those who are still here. So please see that we have covered this three cases for first order higher degree equation. But one thing is still remaining, the Claudius form. That is also a very important one and is included in your first mid-sem. Maybe some of the sections, like Ekesi sir told me, he has already done in his sections, but maybe my sections I have not done.
Exactly,
So we
my
will
section also.
Yeah, so but we have 1 week in hand. One class is sufficient. So in the coming week in the physical class, we will finish this Claudius form. So the syllabus for the first mid-sem will be fully covered in this coming week. Right, sir?
Yeah, quite right. It is a wonderful lecture, as I have heard from very first.
Yes, we can close.
Wonderful
Thanks.
lecture.
Thanks, madam.
Now we can close.
Ma'am?
Thank you, ma'am.
Yes.
Okay,
Ma'am?
thank you. Yes,
yes.
yes.
Ma'am, when we are getting this PDF?
Today itself, after the
Today
class,
itself,
only I
after
will
the
just
class.
share.
Don't worry
Yes,
about it.
you will
beta.
get much more PDF. You will get this lecture. You will get one video lecture that was given by me. Madam will send everything in the Google Classroom appropriately. So don't worry.
Yeah. By
There
today
will be
itself,
no
I will
dearth
share.
of no dearth of study material, videos, and all that. So please keep working.
You have to do practice only.
today's,
That is extremely
uh,
important.
Yes.
And today's attendance highest was around 235. Last time on 4th, there was a Holi in front. In spite of that, the attendance highest was 270.
Yeah.
Today, there is no Holi in front or behind, but the attendance gone. Anyway, it's all right.
Well,
Those who are
okay.
serious have attended.
Obviously.
Can you
Okay.
share the
Thank you.
whole recording of the class?
Yeah, yeah,
Today?
we will do it. We
Yes,
will
yes.
do
We'll do it. Don't worry about all these matters.
Okay, okay.
We'll help you from all aspects, Betty. Okay, that's all for today.
Ma'am,
Good day.
Yes, please.
ma'am, can you please send the syllabus for midterm on math
Yes,
syllabus?
yes. Today itself, I will do that. Everything you will get by today evening.
As we have told now, we'll do everything.
Yeah, yeah. Yeah, I know
After-
that other module syllabus you want. I have asked actually all my co-teachers. They will be sharing with me and then I will post the details in the Google Classroom. Today evening, by evening, I will do that.
We'll do get everything.
Yeah.
Who is the best of
Okay,
you?
ma'am.
Thank you. Okay.
Thank you, ma'am.
Bye.
Thank you.
Okay.
Dean.
Okay.
Thank
So
you, ma'am.
sir,
Thank
we
you, sir.
can close, right?
Okay, yes, please. Bye
Yes.
bye.
Yes.
Good day, everybody. Good day, everybody.
Thank you,
Ma'am.
sir.
Ma'am,
sir.
one question.
Thank you,
sir. Ma'am, is Clairaut's equation in the syllabus?
Yes, yes. Clairaut's equation is in the syllabus that we will do in the coming week. Okay, one lecture class we will all get with you, one physical class. So we will finish that and it will be in the syllabus for the first midterm. Okay.
I've done it in section IJK, those who have come to class in the last week. Okay.
Okay.
Ma'am.
Thank you, ma'am.
Yes.
Ma'am, last semester we had been taught application of Schrodinger equation. In that we had been given the general solution of a particular equation. It was a second order differential equation. That
Okay.
a sin kx plus b cos kx is equal to is a general solution. So how did we get that, ma'am?
See that we will cover, that is in our syllabus, that is as you are talking about second order equation, that we will do after the first midterm. Those things are all there in your syllabus, so we will do after the first midterm, that part. Okay, so just not concentrate on that now, we will do it. Okay. That is we have different solution methods again for higher order equations. Okay. And
Ma'am,
because
there
it's a
is
second
no-
order equation, you get two constants over there. As you are telling, a cos x plus b sin x. So you get two constants over there also.
That is like recurrence relations solving. Solving that is like recurrence relations.
Yeah, we will do it. Don't worry, we will do it.
Ma'am, there is no PDF regarding the vectors, I think.
See, that you have to ask for the concerned teachers. That I cannot help. Vector space you are talking about, right?
Yes.
Okay, let me see. I will.
No, I will comment on this, madam. Let me comment on this. Those of you who are still here, please listen very carefully. It is the PDFs and the PPTs and all that, they are, just not substitute for books. They are only additional material. If you want to get some idea about vector spaces and all that, because after all, whatever PDF anybody makes is after consulting a few textbooks. And the best is extracted. But you have to read the books. Do not think that a video lecture from some class teacher or a PPT will be the enough material to form ideas, to form concepts. You have to study because these are very, very tricky topics. Am I clear?
Yes, sir.
Yes, sir.
Okay, so then we will close now.
Madam, I am leaving now, madam. Mythic.
Yes, yes.
Now all of us are leaving. Chalo.
Yeah,
let's
we
go.
are all leaving. Let me close. So thank you, students.
Thank you very much.
Thank you, sir.
Thank you, sir.
Thank
Good day, sir. Good day, sir.
Thank you.